Right, hello and welcome. It's time to talk about these things. Lambdas, something we talk about a lot. People got very excited in 2014 when Java added Lambdas, kind of one of the last mainstream languages to do so. But what I want to explore today is, well, do we really understand what Lambdas are? We normally think of them as just like a shorthand. Are they truly Lambdas? In the original sense, what is their history? What are they for? And what does it tell us about paradigms and languages as a whole? So let's start off by considering it's a very fine looking Greek letter. It's got a particular characteristic, very distinctive, and it's got associated with a number of things. For some people, when you say Lambda, they think, AWS, which has absolutely nothing to do with Lambdas. Other people visually associate it with half-life, which got its idea from the decay constant in physics. Now, physicists are never one to shy away from reusing a letter, and so they use it as wavelength as well. And of course, there is calculus. Lambda calculus is, of course, the one that we are most interested in today. So Java added them in 2014 in Java 8. How old are Lambdas? 1932. Let's try that. They were invented by Alonzo Church. So basically they are, at this point in time, nearly 100 years old. So he created this kind of system to allow proofs to be made. It's probably better known for the 1936 paper, An Unsolvable Problem of Elementary Number Theory. They weren't really there, although they were there for computational reasons. It's in the same way that people like Alan Turing were looking at things computationally. They didn't necessarily have a device in mind. And there was this specific sense of, we must work out what is computable, what is not. They made their way actually into computing proper. The first language was Lisp that actually properly embraced them. So first implementation of Lisp was 1960. And they've wandered through various languages. Now, for some people, they immediately associate Lambdas and things like that with functional programming. So a number of people often talk about, I'm adopting the functional paradigm, or Java has become more functional because it has adopted Lambdas. Actually, nothing could be further from the truth. Lambdas are not unique to understanding functional programming. They are certainly functional abstractions of a type. But what we will find is that they are far broader than that. They underpin and can be described within many paradigms. And then actually what happened when Java acquired Lambdas. Java's never going to be a functional language because you can't define functions in it. It's kind of simple. You can only define methods. The moment you're allowed to have freestanding functions, at that point, we can start talking about whether or not we can have as actually a functional language. That doesn't mean we cannot adopt functional styles, but that is like any natural language, borrowing in styles and words, but that does not mean that that language is that. It just means we can borrow ideas, but really you can't do the whole thing. So to really understand this, I'm going to do a tour of languages. Most of them are going to be JVM languages. But actually, I'm going to start by stepping outside that. I'm going to go and look at this Ruby tutorial I stumbled across when I was kind of putting together some material on Lambdas. And I kind of liked some of the tone of this and said, despite the fancy name, a Lambda is just a function, peculiarly without a name. This gives us a rather interesting insight. This kind of classic Phil Carlton quote. There are only two hard things in computer science, cache and validation and naming things. So if we go for a Lambda-centric approach, you know what? We've just solved one of the main problems. And if we are talking about Lambdas then, and we're going to talk about pure functional programming, well, pure functional programming has no side effects, and therefore there are no caches to invalidate, which means basically we're having a good day. We've just solved the two main problems in computer science. But let's actually go back to that 36 paper. Church offers us a reasonable definition of this formalism, and he introduces the notation. We select a particular list of symbols consisting of the symbols, curly brackets, great, open parens, lambda, and square brackets. These are all nice and familiar, except the lambda is a bit new, and an innumerably infinite set of symbols, A, B, C, etc., to be called variables. Now, an important point here, sometimes people get a bit confused. They kind of say, well, variables, if I'm doing functional programming or if I made something final, then surely it doesn't vary and the name is wrong. that is not what variable means in mathematics. The term in computing is borrowed in from mathematics, and the idea of something being a variable has existed in mathematics for over 200 years. What it means is that it is not constant, it does not appear as the same value in different uses of a particular formula. It may vary from one use of a formula to the next. That's what variable means. It's not talking about state change in the way that you normally think about it. Now, we define the word formula to mean any finite sequence of symbols out of this list. So he's talking about really grammar. Now, historically, the way people thought of functions is a function is a separate kind of thing. It is somehow separate from all the other things that we may talk about that have values. And so it is not a thing with a value, it's a special construct. So we might write a formula f like this, f of x, takes parameter x with respect to a formula. What we're saying with lambdas is that we are saying, no, if we do bind it, then f, that's not the name of the lambda, I'm just associating a name with it. It's actually that expression, lambda x, over a formula that is the lambda, that this is a functional thing that can be applied to something, and that it is the same first-class citizen as, say, a number or any other mathematical value. So it turns out there are three basic laws of what constitutes a lambda. We can have variables, and we can have abstraction, functional abstraction, and we are able to apply. I can optionally put parentheses in, but we're basically saying, in this case, y is a lambda, x is a parameter, and I can apply y to x. Okay, so these are the three laws. If you've got these three, you've got lambdas, you've got directly. Let's look at a couple of other aspects. One, this is an abbreviation. An abbreviation basically means that we can substitute f for the expression on the right-hand side. So it's a substitution, almost like a macro, if you like. What this means is that you cannot have recursion because you cannot have a thing on the right-hand side that is the same as the thing on the left-hand side. It cannot refer to it because it is a substitute, and the substitution would go on forever. If you want recursion, you need to use a fixed point combinator, which is well outside the scope of this talk, and but is interesting. But there's this idea I can give names to these long formulae. We can also kind of separate out and clarify and classify the kinds of variables we're dealing with. Bound variables, that is bound to a parameter. It's introduced in this context. It will be bound at the point of application. Then we have these free variables, which refer to something outside this expression. That's kind of an interesting thing. We're going to come back to this question of how is that bound a little bit later. So if we take a traditional idea, a traditional function, square of x, so in other words, we treat functions as having a special syntax and a special place in the language, then what does this look like from a Lambda perspective? Well, it looks like this. In other words, there is nothing special about the name square. It simply associates with an expression. We don't have a special construct. So in Java, you're used to, methods, a functional thing. They have a special syntax and nothing else can be mixed with that. So there's a very strong, huge distinction in the type system and the way that you define things. These are not missable. They cannot be mixed easily. They're a different kind of concept. So a fully Lambda-based language makes no distinction in this sense. Now let's go back to something that Church said. Church said, innumerably infinite set of symbols. That basically means that we could replace the X's with emoji. Now, I'm not saying Alonzo Church invented emoji in the 1930s, but I am saying that this is possible. And, we can replace square with square, which I guess means this is a cross product if we look at that. And I can apply it. And that is substituted. I can replace that with this, which is equivalent to this. I'm able to do all of these things. This is first-class lambdas. This is what a lambda is. Now, that Ruby guide says you may have heard of lambdas before. Perhaps you've used them in other languages. Yeah. And actually, if we go to JavaScript, it actually gives us a better idea of kind of the evolution and relationship of these concepts. So sometimes people kind of describe JavaScript as bringing lambdas to the masses. So it's the mid-1990s. JavaScript's coming out, Java's coming out, and Java is almost object-oriented, but definitely has no kind of functional features to it. And JavaScript is actually object-oriented. We might not like the syntax, but it is object-oriented and it fully supports lambdas because I can simply replace this with an expression. In other words, this is kind of a shorthand. It's a special syntax. This is a non-special syntax. Square is simply now bound to a thing that is a functional abstraction. Later on, ECMAScript 6 introduced a shorthand, the arrow notation. Obviously, there are some changes in the syntax, semantics, but the level we're worried about today, I'm going to just say, this is equivalent. And there's a lot of shorthand in the syntax. In fact, to the point that I can get rid of the statements. Now, that's kind of an interesting thing. When we talk about lambdas being expressions, then technically something that uses statements, yeah, that's not really truly a functional idea, but that's fine. We can reduce it to this, and we can apply it, and we can substitute square for that. As long as we're not using recursion, then we actually this all works. When we use recursion or we use named functions, then we're stepping a little bit outside that. But within that broad scope, there is a subset that these lambdas are legitimate lambdas. So let's talk more about these things. What are they? They're anonymous little functional spies sneaking through the rest of your code. Whoa, that's kind of scary. I mean, given all the kind of security concerns, I'm not entirely sure I want any kind of spies sneaking in, but that association with functional programming is really strong. So let's go back to Lisp, and Lisp, unsurprisingly enough, named lambdas lambda. There it is. That's our expression, and we can apply that to a value, and therefore we are going to square 7. On the JVM, the kind of everybody's favorite Lisp-like language is Clojure. Now, why I think is interestingly ironic, and I don't know if the irony is intentional, but it uses a lambda as its logo, but it's not just that the word lambda doesn't appear in the language. In other words, it doesn't use lambda where Lisp uses lambda. It uses fun, because apparently the great vowel shortage of the 1970s and 80s is still on. So it uses fun, and it's an anonymous function. So and some people will say there is a distinction between an anonymous function and a lambda. That is a hair so fine, I'm not going to try and split it today, and I'm going to say these are equivalent. But I do find it interesting that the logo is this, but actually lambdas are not part of the language formally. And yes, Clojure supports this properly. I can apply it to 7, and that's full. So clearly, I've made a really strong case here for these are functional, and this works. These are pure functions, and so on. And other languages don't have lambdas. Well, that's not really the case, is it? Let's look at Algol 68. The first draft of the language was, guess what, 1968. So this is a language that is procedural. It is highly procedural. It is one of the most procedural languages you're likely to encounter, except that it uses expressions everywhere. And yes, it doesn't really have much of a concept of immutability, but it is strongly procedural. Now, most people think, oh, procedural languages, they lack powers of abstraction. That's actually not the case. It's a misunderstanding. They have great procedural abstraction. It's just that many of the procedural abstractions that were encouraged and explored were missing from later languages. In Algol, a procedure is a first-class concept, to the point that I can have, yes, an anonymous procedure. In other words, here's the code. And here we see it again. I can now bind it to a variable. It's got a type it's a formal type within the language. Procedures are a first-class concept, and then I can apply it. In fact, I can replace that expression and apply it directly. So in other words, it turns out that if you're doing procedural programming properly, or rather you have a fully procedural language, and many languages did not support the full model of proceduralism. Pascal, I'm going to blame Pascal for a lot. C had slightly better support than Pascal, but actually a lot of them just missed this bit out. So this is kind of an interesting thing. These are part of the procedural paradigm. Oh, and they're objects. Okay, so wait a minute. I'm telling you that I've already listed off 3 paradigms, and we could keep on going to other paradigms. They're kind of everywhere. They offer an underpinning. They are a fundamental model of computation, if you like. So this is kind of almost parody. It was written a number of years ago. This idea, the venerable master Quicknar was walking with his student Anton, hoping to prompt the master into a discussion. Anton said, "Master, I have heard that objects are a very good thing. Is this true?" Quicknar looked pityingly at his student and replied, "Foolish pupil, objects are merely a poor man's closures." Now, this is based on a kind of a character that Guy Steele developed. And Guy Steele was one of the developers of Scheme. very Lisp-based, a tidied-up Lisp, if you like. And there are a series of papers, the Lambda, the Ultimate papers, which explored the power of Lambda-based computation. And they were called Lambda the Ultimate because Lambda was always the ultimate way of doing stuff. You know, there was always a way of expressing something in Lambdas. You could always reduce it to that. And the mathematical purity immediately puts one into the space of thinking in functional programming. But the interesting thing is that all the paradigms were described using this, including this idea of closure, which is often kind of pops up. And this was an interesting one. Concept of closures was developed in the 1960s for the mechanical evaluation of expressions in the Lambda calculus. What do you do with those free variables? You need to bind them in somehow and in a regular way. Peter Landin defined the term closure in 1964 as having an environment part and a control part. So in other words, we've got this idea of capturing the environmental, the state, the values, and then the behavioral aspect. Joel Moses credits Landin with introducing the term closure to refer to a Lambda expression whose open bindings, those free variables, have been closed or bound in the lexical environment, resulting in a closed expression or closure. This usage was subsequently adopted by Sussman and Steele when they defined scheme in 1975, a lexically scoped variant of Lisp, and became widespread. That's the usage of the term closure. So for some people, sometimes they discuss what's the difference between a lambda and a closure. Sometimes people talk about closures being a subset of types of lambdas. A lambda, if it binds something in, then it is a closure. If it's just a free lambda, if it's a lambda that has no free variables, then we'd just say, yeah, it's not a closure because it doesn't close anything in. Chastised, Anton took his leave from his master and returned to his cell. Intent on studying closures, he carefully read the entire Lambda the Ultimate series of papers and its cousins, and implemented a small scheme interpreter with a closure-based object system. This is kind of the book that we often refer to as becoming one of the scheme books, a kind of computer science classic by Abelson and Sussman. And in that book, there's this kind of nice homo-iconicity of an evaluation function, the fundamental eval function. This was actually present, a version of this was present in the original Lisp book that I showed earlier on. And the idea is, here is the heart of scheme defined in scheme. Therefore, if you were to create a portable scheme system, this is the bit you have to translate into whatever your native system or your other programming language is. So in other words, this is how to interpret scheme based on scheme. And there's how you interpret a lambda. Now, why did they build scheme? This is from their history. This work developed out of an initial attempt to understand the actorness of actors. Actors were developed in the early 1970s, 1973, by Carl Hewitt. They recently enjoyed a kind of a surge in popularity and a more widespread adoption than they ever saw before. And their goal was to try and understand it, because Carl Hewitt's descriptions of it were not entirely clear. So this interpreter attempted to intermix the use of actors and Lisp lambda expressions in a clean manner to really try and understand it. And alongside lambdas, they introduced actor expressions, which, if I remember from a talk I saw Guy Steele do about 15 years ago, he called these alpha expressions. And what they discovered was that actors and lambda expressions were identical in implementation. So let me just kind of hack together what it would have looked like. Basically, here's what I showed you before, and here's how you interpret alpha expressions. So if you look here, this is, if the expression is an alpha expression, do the following. If the expression is a lambda expression, do the following. As you can see, the code is identical. And as everybody knows, don't repeat yourself, try. They discovered at this moment that the evaluation model was identical. Boom, there was a beautiful flash of light and a moment of unification. On his next walk, with Crooknar, Anton attempted to impress his master by saying, "Master, I have diligently studied the matter and now understand that objects are truly a poor man's closures." Crooknar responded by hitting Anton with his stick. "When will you learn? Closures are a poor man's object." At that moment, Anton became enlightened. Of course, there are some real issues about workplace safety and HR policy here, but there is this idea that we are looking at this the wrong way. And 2009, William Cook, revisiting a data abstraction paper, a very significant data abstraction paper from the mid-1980s, made the following observation. Lambda calculus was the first object-oriented language. So this goes back to the 1930s. because of its relationship of behavior and state and how you can then pass that around. So if we look at a stack, and I'm going to do this one in JavaScript, we can actually do the whole thing just using lambdas. And this idea of binding in state and closure, the idea of private being truly private. So if I create a function that generates a new stack, I'm going to return a Cartesian product, a named set of fields, basically an object to you or me, but the idea is here are named fields and they correspond to lambdas that have closure over a local variable. In other words, this variable is so private that it cannot be seen. It's hidden within this block. And so therefore, we're returning a set of operations that is bound to change an operation on a private variable. That variable lives on beyond its block. And this is actually turns out to be a foundational idea in structured programming, block structured programming. As it's described, one of the most fundamental ideas, a procedure which is capable of giving rise to block instances which survive its call will be known as a class, and the instances will be known as objects of that class. So this is in structured programming. Ule Johan Dahl, one of the joint inventors of Simula 67, and Tony Hoare, talking about hierarchical program structures. Now, when many people think of structured programming, they tend to think of go-to and control flow. Turns out structured programming was kind of what it says. It was about structure, and it wasn't just about a control flow structure. They also talked about structures which were not available in many of the languages people were trying to apply the techniques to at the time. So people were trying to do this stuff in Fortran and in BASIC and in COBOL. They don't have this kind of construct. They don't even have basic data abstraction. So in other words, this book, which dealt with control, or this movement, some of which was captured in this book, which dealt with control flow, data organization, and all of the relationships that we can have, most people just, well, they couldn't apply the data abstraction stuff. So we remember it for the control flow. Now, what we see here is a broad multi-paradigm nature. And in the book I edited with Trisha G last year, 97 Things Every Java Programmer Should Know, the late Russell Winder made this observation in one piece. The JVM is a multi-paradigm platform. Use this to improve your programming. Now, there's an observation here that's quite important. Although originally introduced as an object-oriented platform for the language Java, Russell says the JVM is a multi-paradigm platform. He's not making the claims about any of the individual languages. So he's not saying Java is a multi-paradigm language. He's saying the platform is, and we can actually see this in many of the languages that are supported on the JVM. So let's kind of explore a few things about the notation and the consequences of some of the design decisions. As Richard Feynman, the Nobel physicist, observed, we could, of course, use any notation we want. Do not laugh at notations, invent them. They are powerful. In fact, mathematics is to a large extent the invention of better notations. So we got lambda. Where did the letter lambda come from? Well, lambda over a. Originally, apparently, well, there's a couple of stories. The one I like, I can tell you one I like. The one I don't like is the one where Alonzo Church later in his life said, oh, I just like the look of the letter. There was no specific reason. But earlier in his life, he said, actually, there was a reason, so perhaps he forgot as years went by, is that originally he wanted to use a caret. Just, in other words, abstraction over A. But as he was American, you know, if this had been typeset in France, there'd have been no problem at the time. But the typesetters weren't too keen on this, so they said, well, what about doing this? I said, well, that looks like the letter lambda, and lo and behold, there we have it. Now, what do we end up with in Java? Well, we end up with an arrow. Okay, so here's our square. Now there's a problem. In fact, there's quite a few problems. Java took a departure from its historical roots. Historically, and indeed still in many languages, nothing to do with the C family or anything like that, there is an idea that every expression has a type. Java breaks with that. This expression does not have a type. And that's actually a bit of a problem. Now, some people might say, well, no, it's a poly expression as opposed to a standalone expression. Yeah, kind of poly expressions were introduced for a different reason. They're a bit of a hack when it comes to Lambda. They actually dodge something fundamental. Java does not have a type for Lambdas, because at this point, I can describe the idea of a poly expression is that it basically, we have not been able to deduce all of the type information. So let me tell you in English what is going on. What I am seeing on the screen is this is a Lambda expression that takes one parameter x of type that is not yet known, and then multiplies it, which therefore constrains it to be of numeric type. So I don't know at this point if it's an int, a short, a double, so on. I don't know whether the return type is an int, a double, whatever. In other words, you can see that there's an open aspect, but I've just told you exactly what it is, a Lambda expression. Tell me what Java, so remember, poly expressions were introduced for generics, in other words, incompletely able to specify a type. Here, I've just been able to tell you exactly what it is, Lambda expression. Go and look in the Java spec and in the library and go and find the type for lambdas. It's not there. In other words, lambdas aren't actually properly a part of the Java language. There's kind of this workaround where we pretend, it's not complete. If I replace this with a zero parameter lambda that had just a block, I'd be able to tell you exactly it's a parameterless thing that returns void. I've closed all the types, but apparently it's still a poly expression. If I try and apply this, then I could tell you what I would expect from this. It won't compile, hence why it's red. I would expect this returns 7. We have now closed out all of the types. This is a Lambda expression that applies to integers. We've deduced the type of x to be an integer, therefore the return type is an integer. I've just told you all the type information. I've told you in English, but I cannot tell you in Java because lambdas aren't really a proper part of Java, the Java type system. They're kind of a bit of a bolt-on. Now, there are historical reasons for this, but this has some interesting consequences. I can't write this syntax because they are not function concepts of any kind. I have to then go through a binding. I have to take a lambda which has no type and then bind it to something using a form of magical conversion, of which there are a number of predefined and available features in Java util function. In fact, there's quite a few. And this is a bit of a nightmare because it immediately blows away any regularity and concept of functional consistency and abstraction. I mean, some of the names that we have available for calling or applying one of these expressions are these. Now, these are not dedicated to lambdas, so I haven't given a lambda a calling syntax. I've taken a lambda, magically converted it through means which are unspecified and are based on conformance that cannot be properly described within the language at the level of the compiler for types that cannot be represented within the runtime system, a set of syntax, and I've made them into objects. And when I take this, in other words, I have to do this. And this unfortunately means that we go ahead, call them lambdas. I call them lambdas, but it's like a proper name. It's a name. It's Java lambdas. They're not really lambdas because the one thing we can't do is apply them. Okay, so there is an interesting distinction there. Now, one of the other things I find kind of interesting is that when people kind of talk about functional thinking and so on, they're a little bit disappointed to discover that Simon Peyton-Jones observes, and he's most associated with Haskell, that actually those people in your accounts department have been doing functional programming for longer than you have, in all probability. Excel is the world's most popular functional language. Now, strictly speaking, it's not Turing complete. It is a declarative language system. It is a data flow system. And functions are not truly first class, so we may argue with whether or not it's truly a functional language. Well, we may have argued up until the end of last year. I used to joke about the fact that, imagine if Excel had lambdas. I mean, what a nightmare. Guess what? Excel now has lambdas. So they allow you to define new functions, and they are, truly lambdas. We've got something that's Turing complete. These are true lambdas. They can be arguments to other lambdas. You can define church numerals. Interesting, we'll come back to those. Lambdas can return lambdas. You can do currying. You can do fixed point combinators. In other words, do recursion, and hence write recursive functions. So, okay, that's kind of scary and kind of interesting, possibly even cool. So let's go back to that paper. That paper from 1936, an unsolvable problem of elementary number theory. What I find fascinating about this paper is Church was trying to prove something about numbers, and integers specifically, so natural numbers to be even more precise. But what's interesting is that the number system's too complex. So what he did to do this is he actually got rid of numbers. He basically said, that's too complex. I'm going to do everything with lambdas. That was the whole point. He got rid of the whole number system and recreated his own numbers. So this is kind of like software, extreme software craft. You're going to craft your own numbers. You're going to craft your own zero. You're going to craft your own ones, and therefore these are handcrafted, beautifully lambda-based numbers. And this is a Church encoding. So 0 is this. It's not obvious what's going on. 1 is this. Again, it's still not obvious. We've got a lambda of f over a lambda of x, and then we return x. Then we've got a lambda of f over a lambda of x, and we return f of x. It perhaps becomes a little more obvious when we look at number 2. F appears twice. Lambda of f over lambda of x, f of x. And 3, 3s, 4s, 5s, 6, I get what you're doing. Now, one of the things is that strictly, lambdas are really about taking one parameter and yielding one result. But having multiple parameters is so common that there's a shorthand for it. We can also throw in other shorthands. We could basically count the number of applications, and we could write it like this or even like this. And now you see what's going on, that we are representing numbers. We've created numbers, that numbers are not Platonic entities, they are applications. So 3ness is applying, is taking something and then applying something to it 3 times. Well, not just 3 times, but applying something to the result of applying something to the result of applying something. Like, in other words, we count the number of applications. 0 is not applying it and just yielding the original parameter. So in other words, it is a description of numbers in terms of process or application. Now, this idea of church numerals actually does sneak through in a couple of languages. So in Groovy, I can take the integer and you think, oh yeah, it's just an integer, it's an int. Actually, it's got methods. Actually, one of the methods is times. And therefore I can pass in a block of code, which is itself a lambda, in effect. What we're doing is we are exploiting 7ness. We are going to take this block and do 7ness to it. That means it gets applied 7 times. And this idea can be, Groovy borrowed it from Ruby, Ruby took it from Smalltalk. Smalltalk uses church encodings for numbers. It treats numbers as a first-class thing that relates to quantity and process, or doingness, if you like. A 7 is not just a number, it is the doing of something 7 times. So when we apply this, we get this, which is kind of cool. Now, let's go back and treat this a different way. What does SUCC suck? Does it suck? Well, what's going on here is I can define this differently. 1 is the successor of 0. 2 is the successor of the successor of 0. Oh, okay. So in other words, we've got this applying this going on. And we can shorthand that. Or we can recognize, well, 1 is the successor of 0. 2 is the successor of the successor. Well, that's the successor of 1. I can write it like this. Now, the way you write the successor code is like this. So that's interesting. It turns out you can do all of this. You can turn it into JavaScript really easily. Now, obviously, we have to put _0 because it turns out JavaScript's already taken the numbers. And we can write it like this. And we can capture that abstraction. And JavaScript actually offers us a very convenient syntax. It's syntactically light for this. And so we can do that. And therefore, we can do 0ness. Now, what I'm going to do is I want to take an expression. I'm going to pass in something that 0 is going to do something with. Now, you've got to pass in something that's going to happen. In the pure Lambda system, there are no numbers. Okay, in or the original untyped Lambda calculus, there are no numbers. The numbers are created. The only kind of thing is a lambda. Everything is lambdas. So you're applying lambdas to lambdas. Here, I'm going to deal with everything in white is basically the Lambda system we've created, the church numeral system. Everything in green is something I'm passing in from outside. So I'm going to use ordinary arithmetic. I'm going to pass in a lambda that takes a number n and adds 1 to it. Okay, I'm going to pass that in. So then what am I going to do? Well, that yields a lambda, which I can then apply to something. And I'm going to apply that to a regular 0. And the result of this is 0. Well, this is not very impressive so far. Let's do this now with 1. And we get 1. And then with 2. It turns out what's going on is we are applying the thing in the first brackets to the thing in the second brackets, 0. We are applying this +1 relationship based on the underscore value. In other words, _5. In other words, the 6ness is being applied. What is the 6ness of n + 1 against 0? Well, that is 6. In other words, we've just recreated numbers. It's kind of, this is for those of you watching mathematically, we've taken the Peano axioms, lambdaed them, and now we are taking them back and showing that we've invented iteration, basically, and iteration is embedded within the numbers. Now, what's kind of cute about this is that I can now take this and I can say, well, that was normal arithmetic, but what if I use strings? Well, we've just invented unary. So in other words, n plus 1 against an empty string creates a successive relationship, 1, 1, 1. So unary, you might be familiar with binary. Unary is the number system of the universe. One planet is one planet, 2 planets is that planet and that planet, 3 planets is that planet, that planet. In other words, it's not a very compact system. If you have 1,000 things, then it's 1,000 digits. So let's go back to square. How can we write square? Turns out square can be written like this. It is 2ness applied to something. Give me a number and I will apply it itself times. So square of 7 is the 7ness of 7. Okay, we're going to apply that twice. If I were to put _3, that would have been the 7ness of 7ness of 7. Now let's give that to that, give that to that, and the answer you've been waiting for all this time, 7 squared is 49. So what we see here is, through this tool, we have learned a little bit more about paradigms are more unified, are both more unified and more distinct than we thought in some ways. That lambdas are very fundamental. If they are very pure, you wouldn't really want to be programming with them in their purest form. That's hardcore. And this quote from Andrew Koenig: people who brook no compromise in programming language, such as programming lambda calculus or machine language. Actually, if you really don't believe in compromise, lambda calculus, because machine language is based on 1s and 0s, and you can make your own 1s and 0s, is the one thing that we have learned. But when we start looking at other languages, we start realizing it raises questions about, we use lambdas because they're kind of practical. They give us a kind of simple closure, a way of passing blocks of code around. That is the convenience. So where in almost all the languages we're using, they're not really pure lambdas. Some are more pure than others, but certainly in the Java one, lambda is just a name. And there's nothing wrong with that, but we do run up against the differences every now and then, and those are issues of convenience for which there is a historical context and reason. I hope you found this helpful.